Hi friends, we are going to start with the hydraulic machines. That is the fifth unit. Up till now we have covered the sixth unit, that is boundary layer theory. Now here we will start with the next unit, which is nothing but the continuation of fourth unit, that is impact of jet. Now here we are going to have an application of hydraulic impact of jet in hydraulic machines. Now there are two types of hydraulic machines. One is turbines and another one we are calling it as a pumps. So what are the turbines? These are nothing but machines which convert one form of energy, that is hydraulic energy, is converted into mechanical energy, and then afterward mechanical energy is converted to electrical energy. So that is a simple way of conversion by means of turbine, and then we'll get electricity. The example of it is nothing but a hydropower station. So turbines are used in hydropower station. On the other hand, the pumps which we are using at our home, we are simply switching off a button, that is electrical energy, is converted into the rotation of the runner, that is mechanical energy, and then due to this mechanical energy the water is getting pumped at a higher height, so that is conversion into hydraulic energy. Now here we'll see simply the layout of this hydropower installation. Now you can see that this is a gross head. Now you can see this diagram. Hydropower installation is simply like this. Hydropower plant consists of a dam. On either of side of it there is a reservoir. The headrest is there, and this is the bottom or tailrest. The difference between these two is called as a gross head, Hg. It is denoted by Hg. Then water is allowed to move from higher height to the lower height, and due to this sudden change in the water level or level of the ground, the water will run fast, and if you allow to put this electricity velocity of water on these vanes of turbine, then the turbine vanes will get rotated, and that mechanical energy can further converted into the electrical energy by means of generators. So HF is nothing but the head loss due to friction. When water will move through this penstock, there will be friction between the water and the internal circumference of penstock. That is denoted by 4FLV square by twice GD, which we have seen in case of flow through pipes. And how we can find out the net head is nothing but the total, that is gross head, minus the head loss due to the friction. So H is nothing but Hg minus Hf. Velocity is given by square root of twice Gh. So net head is here. The turbine, it is having a vane. This is tail rest, this is head rest. So this is how the hydropower installation is done. Now next is we should know what is the efficiency of turbine. Now we are knowing that the usually efficiency is given by output upon input. Now anyone, for example, if we'll take a student who is having a say if we'll consider input is his hard work and output is his marks. So within a less hard work, if the better marks if he is getting, then we can say that he is more efficient. Similarly, for turbine also, we are having a different kinds of efficiencies, which is nothing but the output upon input. So there are usually four types of efficiencies: hydraulic efficiency, mechanical efficiency, volumetric efficiency, and overall efficiency. So what is hydraulic efficiency? Now if we'll consider a turbine, it is having a different component, that is just like a runner, shaft. So these are the two main components, and water will pass through this shaft and it will impact on the runner. So whenever we are finding out the hydraulic efficiency, we are having a ratio of power delivered to runner to the power supplied at the inlet. So RP upon WP. Okay. Then similarly, for mechanical efficiency, it is nothing but the power at the shaft of the turbine to the power delivered by water to the runner, SP by RP. Runner power is denoted by RP. Water power, that is water supplied, that is denoted by WP. Then shaft power is denoted by SP. And again, power delivered by the water to the runner is denoted by runner power, that is RP. So mechanical efficiency is SP upon RP. And next is volumetric efficiency. Now it will be in terms of volume. So how much volume of water actually striking the runner, and what is the volume of water actually supplied to the turbine. Now here we can say that the frictional losses will reduces the volume of water. That's why volume of water actually striking will many times will be smaller than the volume of water supplied to the turbine. This depending upon the frictional losses or any another kind of say losses. Maybe leakages will be also possible in the penstocks. Then overall efficiency is volume available at the shaft of turbine to the power supplied at the inlet of the turbine. So shaft power upon water power. SP upon W. So whatever the numerator of second mechanical efficiency and denominator of first, that is hydraulic efficiency, its ratio is nothing but the overall efficiency. So we have to consider hydraulic and mechanical both efficiencies to calculate overall efficiency. So we can simply say that SP upon WP. Now I can again multiply and divide it with runner power, SP by WP into RP by RP. So SP by RP is what? It is nothing but mechanical efficiency. So eta M, and RP upon WP is nothing but the hydraulic efficiency, that is eta H. So overall efficiency is given by eta M into eta H. So this is all about the efficiency. Okay guys. Now next we'll start with the actual concept of hydraulic turbine. Now in this we are going to cover all these topics, that is classification of turbine, selection of turbine, design of turbines. In design of turbines we are having three types: Pelton, Francis and Kaplan turbine. Then fourth one is draft tube, surge tank, governing of turbines, unit speed, unit discharge, unit power, and this three you can read it out. That is characteristic curves of hydraulic turbines, similitude or model analysis. This we are not having in detail actually. And the last one is cavitation. So we'll simply have the classification of turbine. According to the type of energy at inlet, there are 2 to 3 turbines. You just read out this. I am giving a time for it. So according to the type of energy at the inlet, there are 2 types of energy we can provide, that is pressure energy and kinetic energy. So impulse turbine and reaction turbine. Impulse turbine, the example is Pelton wheel, and it requires high head and low rate of flow. Reaction turbine requires low head and high rate of flow. So The example is Francis and Kaplan. Then second classification is based on according to the direction of flow through the runner. Direction of flow may be of four types: tangential flow turbine, radial flow turbine, axial flow turbine, mixed flow turbine. Tangential flow turbine is Pelton wheel, radial flow is Francis, axial flow is Kaplan, and mixed flow is modern Francis turbine. Okay, then next, again this classification already we have discussed, that is reaction and impulse. So reaction are Francis and Kaplan, and impulse is Pelton. Now we can see the basic difference between impulse and reaction turbine, means Pelton and Francis or Pelton and Kaplan difference. In impulse turbine, the buckets are fixed at the periphery of the, say, runner, moving buckets, or we can call it as a curved vents, and the jet is impacted on it in tangential manner. These buckets are moving. So this is, the nozzle is fixed and buckets are moving. So this kind of flow is there. You can see this diagram, right? The rotor is rotating due to the impact of jet on it. And on the other hand, on reaction turbine, the nozzle is rotating. Nozzle is also rotating, and due to which the flow is simply like this. You can see that it's not impacting at the inner center of the wing. It's simply passing maybe tangentially with very high pressure. The pressure is generated between the blades. Here no pressure is generated. Only kinetic energy is applied. So this is about the basic difference between impulse and reaction turbine. Then the third type of, or third point related to the classification is according to the head at the inlet of turbine. High head turbine, medium head turbine, and low head. High head means Pelton wheel, medium head is example is Francis, low head is Kaplan. Then according to the specific speed, low, medium, and high specific speed, Pelton, Francis, and Kaplan are the basic types of this low, medium, and high specific speed turbines. Then next, classification according to the specific speed of turbine. Now here they have mentioned the speed actually. It is 10 to 20, 20 to 28, 28 to 35 for Pelton, slow, normal, and fast respectively. And similarly it is given in the Francis also. And for Kaplan it is the highest one. Since per minute the rotations are in between 300 to 1000. It is the highest one. Then classification of turbines according to the disposition of turbine shaft. There are two types, that is horizontal shaft and vertical shaft. Horizontal shaft is Pelton wheel and vertical shaft is Francis and Kaplan turbines. Now here we'll see what is the Pelton wheel turbine. Actually, you just observe this diagram. This we'll discuss in the next video. I think this video is almost about 14 minutes. So I think up till now you just can see that this is an introduction to the hydraulic machines. You just go through this, then we are going to discuss all the kind of turbines in details after this. Thank you. Thank you very much.